Good afternoon, everyone. Welcome back to E304. In this set of lectures, we're going to start talking about Chapter 6 in our book, which is a chapter on nanoelectronics. So we're going to start dissecting the electronic properties of materials. So in order to do that, we need to look at the electrons and electron energy bands in these materials. So let's remember from Chapter 3, we talked about atoms and electrons having quantum numbers. So I hope we remember that there were 4 different quantum numbers: the principal quantum number, which told us the electron's energy; the azimuthal quantum number, which told us the electron's angular momentum; the magnetic quantum number, which told us the electron's magnetic moment; and finally the spin quantum number. Okay? And we might remember that only discrete levels were allowed. So no 2 electrons could have the exact same 4 quantum numbers. We also remember that electrons exist in orbitals around the nucleus of the atom, and these quantum numbers define the orbitals. Each orbital has 2 spin states, a spin up and spin down state, and no orbital can have more than 2 electrons in it. Okay. So that's a single atom. Now what happens if we look at bringing together multiple atoms? So let's say we have one atom here and it has its electron cloud around it, and electrons are in their orbitals. And then we bring another atom close to it, and this atom has its own electrons that form the orbital cloud around it. Now, as we bring these atoms close together, these orbitals begin to overlap. So you have these orbitals, or these electrons, that when separated would exist at the same energy levels. But as you bring the atoms closer together, something has to happen, because you can't have 2 electrons with the exact same energy, with the exact same quantum number. So something must happen. So when you bring more and more atoms together, what happens then? Well, let's take a look. So let's focus on this slide in the top left-hand corner here at this plot. So this plot is energy on the y-axis and separation between atoms on the x-axis. So we can see that 2 atoms, when they're far enough apart, have the same energy. Okay? Well, as the atoms get closer and closer together, we can see that the energy bands split. Okay? Because as the orbitals overlap, they sort of have to push each other out of the way a little bit so that they don't have the exact same energy. And so since no 2 electrons can have the same exact 4 quantum numbers, the energy levels end up splitting as the atoms are brought together. And in the case of if we had 8 atoms that were brought together, then the energy levels would split into 8 different sublevels. Well, if we brought together a zillion atoms, then we would have a zillion sublevels that were very, very closely spaced, but yet individual levels. And these levels are very close together, and we start referring to them as energy bands instead of individual energy levels. So we begin seeing these bands of allowed energies where electrons can be. So let's look at a very specific example, the energy bands in sodium. So in sodium we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. Well, we can see that there's an energy band is created for each energy sublevel. So we have a 1s energy band, a 2s energy band, a 2p energy band, and then a 3s energy band, and we see that that's half filled. Okay? So let's look at another example, and this is the example of silicon, where silicon has 2, 4, 6, 8, 10, 12, 14 electrons. Well, in silicon what happens, you have the 1s, the 2s, and the 2p band, but here in the 3s, 3p orbitals, something sort of strange and unique happens. These two orbitals form a hybrid sp orbital. So the two, you get 4 filled states in the low sp hybrid band. This is called band hybridization. And you get 4 empty states in the high sp hybrid band. So between these two bands there is some band gap, so there's some energy where no electrons can exist. And this is what's called band hybridization. Alright, so let's move on. Let's look at these bands and energies a little bit more carefully. So in any solid, we see a band structure, right? So we bring many atoms together and they create a solid, and we have some filled bands where there's, they're filled with electrons, and then we get to a certain energy and we have the last band that has any electrons in it. So the last filled band is called the valence band, and it could be partially filled, it doesn't have to be fully filled, but the last band, the highest energy band that has some electrons in it, is called the valence band. And then above that, the first band to not have any electrons in it is called the conduction band. So if we go back to our silicon model here, we can see that, okay, this low sp band, here we have our valence band, and here we have an empty band, our conduction band, and the distance between the valence and the conduction bands is what we know as we define as the band gap of the material. Okay, so the band gap is this distance between the valence band and the conduction band. Okay, well, great, so why do we call it a conduction band? What's the purpose and what does it do? Well, electrons, in order for them to move and conduct electricity, of course, we know electron flow is what causes current flow and electricity to be conducted. They have to jump between individual levels and move in a certain direction. And it's much easier to move in a band that has a lot of empty spaces. So that's why we call this the conduction band, because when electrons get pushed up into that conduction band, that band is mostly empty, so there's a lot of space for them to move and conduct electricity. Okay, so let's talk about these conduction electrons. At room temperature, some electrons jump from the valence band to the conduction band, and these electrons can then move in the conduction band and they carry electric current. Okay, so electrons can jump from the valence band up to the conduction band across this band gap, and when electrons are in the conduction band, then they can move and conduct or carry electric current. So let's differentiate now between different types of materials, conductors, semiconductors, and insulators. And the way that we define the difference between these types of materials is in their band gap. So an insulator, on the far right hand side here, in an insulator, the band gap is really large, and the valence band is full and stable, so you don't see electrons really jumping up to the conduction band very much, so this is why you don't have conduction in insulators. In semiconductors, the band gap is much smaller, and generally the band gap is something less than 3 electron volts. That's the definition of an insulator. So thermal energy or other types of excitation can boost electrons across the band gap in a semiconductor, and then those electrons can be used to conduct. And in a conductor, the conduction and valence band, they are basically overlapping, so it takes almost no energy at all to get electrons out of this valence band and into the conduction band, which is why conductors like metals obviously move a lot of electrons, and you can move electric current very well through them. That's why they're called conductors. Okay, so this concept of the band gap is how we define the difference between insulator, semiconductor, and conductor.